Okay, so here we have some data that shows these patients with diabetes, and they have to measure, what's called their plasma glucose level. I'm not, an expert on this stuff, but looks like they got to measure it every 8 hours after fasting, and then they take another measurement at their checkups called HbA. This is basically the percent of red blood cells that have a glucose molecule attached. And, they do this, over several months. And here we have the data of these 18 subjects who are, in this, study with their HbA in percent and their FPG in milligrams per milliliter. So what we want to do is understand not only, the relationship between these two variables, but what outliers can do to least squares regression analysis or just statistics in general. Like, what would it do to like the correlation coefficient, the coefficient of determination? What would it do to the slope, the y, like things like that? So we want to see what's going on. So here's your scatter plot of the data. Make your scatter plot with the same scale as mine. That way it can match up perfectly. So go ahead and pause the video and make it so that your points are going by these same scales if you can. And then when you got it done, go ahead and unpause it. And then what we're going to do here is, analyze this, but use our, technology. So we're going to enter the data in our calculator. So we're going to go stat, calc, let's go. Well, let me just show you that I already have. Remember, we got to enter in our list. I already have it in list 1 and list 2. So go ahead and make sure you enter it in list 1 and list 2 before you go to the next step. After you do, go to stat, calc. Then we're going to use the linear regression analysis where we have the a plus bx form. And this calculator, I'm going to have to enter L1, comma L2. Let's enter. And see, it's going to give me my A, my B, my coefficient of determination, and my correlation coefficients. So I would have an equation for my predicted y value, but that would be about 66.43 plus 10.41x. So we're going to plot this line on our scatter plot, and then, compare it to what least squares regression lines would look like when we take away these points in parts B and C. Let's first go ahead and let's just write this out down here. I'm going to mention, so this is going to be our original least squares regression line. So y hat dot 66.4 2, 8, 5, 12 plus 10.40768345x. Probably don't have to be that precise, but I just like writing numbers. And remember, when you're plotting lines, I just pick values it would go through. So like, I'll pick x is 6 and then x is 20. Figure out what the y values would be based on that equation. So, I plug in 6 into this equation for x and calculate y. Approximately, it doesn't have to be perfect. 6.43 plus 10.41 times 6 gives me about 128.9. Let me see what it would be when x is 20. 66.43 plus 10.41 times 20, about 274.63. So it goes through those 2 points, so I just need to have little markings there. 6, about 128.9, so maybe something like here. And then 20, 274, maybe on here. It's 275. Plot this line. greater than least squares regression. Now, let's also write down the R and R squared value, and then make sure we describe it. And let's we practice what we got to do when we're talking about a set of quantitative data. So remember, I mentioned the direction, form, strength, and any potential outliers. So we can say that there's a moderate positive linear association linear association between HBA percentage and geez, that's not quadrant and FPG. Remember, mention any outliers because there appears to be 2 outliers here. So let's mention that there, because that's essentially what this problem is, getting at anyways. So let's just mention to be sure that there appears to be 2 outliers. Here's the key thing if you want to recognize is that we have outliers in different sorts of ways, meaning that we got an outlier way over here, like to the right, but close to a line, but just far from all these other points. And we got an outlier way up here, way above them. So we want to see like what would these outliers do if they were, not there? Would like the equation change by a lot? Would the R value change by a lot? Would the R squared value change by a lot? That sort of thing. We want to see like how it actually affects it. So let's also make sure let's write down the R value here just so we have a reference. So the R squared was about 0.32 we saw, and R of 0.4819. So we want to see what would happen to these values in all these statistics we say. So we're gonna focus in part B by looking at subject 18, which is the outlier in the X direction. So this one over here, this guy that we got in purple. Subject 18. Now, to give you some intuition on how this works, we're gonna calculate the mean of X and Y. I'm gonna explain why in a minute, but remember, let's go to our calculator. We're gonna go to calc 2 variable statistics, L1 and L versus L2. And see, we're gonna get the X bar is about 9.31. Let's write that here. And Y bar is about, let's scroll down, is about 163.3. 163.28, we'll just write it like that. Now I'm gonna use a special color that I rarely use. Rare occasion, so this is a big deal. Why I want to find these is I want to draw where the what we call in physics the center of gravity, like where the mean where the mean of X and the mean of Y both meet. So we're going to draw a vertical line through X being 9.31. So about like here and here, or maybe a little more. Do that. And draw a horizontal line where Y is about 163. Now you can see that, this is, dividing, scatter plot into four, four regions. And, what am I getting at? Like, what's going on here? Well, you want to start to think of, these points as kind of being weights. And I like to say like a seesaw, like a teeter totter. And you want to think like, oh, if this is like your teeter totter, and it's going to balance at the center of gravity here. So if you were to take like, points off at this end, you would see, oh, it's going to tilt more up, right? If you were to put more points here, it would kind of like weigh down, right? And let's and points over here, if you took them away, maybe go up. So I want you to start kind of thinking like this, because that's going to let you understand what taking this point or adding this point does, and same thing with here. Because this stuff is, it's something where I can't show you, you can't learn steps on how to, answer these questions. You have to just think about these. And you're going to get questions on your AP exam, multiple choice questions, where they're going to really test your knowledge like this. And I want you to think like this. Think of the center of gravity like that. So going back to part B, before you actually do the, the calculation you're calculating, really think what would happen to the equation if you took this point away. What would happen to this equation? What would happen to the y-intercept, and what would happen to the slope? Would they change a lot, change by a little? Would they go up, go down? What would you think? Once you have an idea in your head, go ahead and let's look at our data now. And we're going to delete subject 18 from both lists. Make them vanish. So delete and delete. Now we're going to run the linear regression analysis with the data, with the subject 18 gone, and let's see what happens. Here we go. See, we have our slope went to not our slope, our y-intercept went to 52, and our slope went to 12. So, they decreased. It decreased. Well, they didn't both decrease. I mean, the y-intercept decreased, but the slope increased. The slope increased. So what had happened with subject 18 is, it went like this. It kind of went a little more tilted. The line, went from being this to, maybe we'll do like this. Let's do it this way. From here, take away 18. It's no longer being weighed down over there. So it goes like that. That's the idea. And that's what you want to recognize. So again, if you take away that purple line is kind of, or that purple point is pulling it down, and it went like this. Slope went up, but the y-intercept will go down because the left side of the graph goes down. I'm going to write this down. I'm going to have it all a formal answer for you to copy, but let's just move on to part C, so we can just do that first, and you can see my answer and how you would want to write it on a free response part. So now we're going to see what would happen with the blue point. Again, think before you run this calculation. What would it do to the y-intercept and slope? What would it do to all that, the R value? What do you think would happen? Once you have an idea in your head, in your calculator, we're going to go back and we're going to add 0.18 back. Let's first add 0.18. That's 19.3. 255 over there. Oops, and that's back in there, but now we're going to go up and delete subject 15. Bang, he's gone. Subject 15. And bang, he's gone. Now let's go and calculate our linear regression. L1, come to L2, and let's see what happens. And here you go. Your new y-intercept is 69.5 about, and the slope is about 8.9. So again, comparing this to the original least squares regression line, again, right here, you're going to see the slope went down by like a little more than 1.5. But The y-intercept went down from 66, or sorry, went up from 66 to 69. So it changed again, but it changed in a slightly different way. The slope didn't change as much as it did. Well, actually changed by about a little more than like 1.5. And think of it now, let's think about why. Like what this point is doing is if the line goes from here, what this is doing is kind of just pulling the line up like it. But since this point is close towards the mean of x, it doesn't really like tilted much. It kind of just like, think of it just like you're just actually gonna do it this way. You're just dragging the line up or dragging it like down. You're not like spinning it or tilting it, because again, when you have points like if you had points on this or this, it wouldn't really, again, affect the way the line is tilted. Again, think of it like a balance beam. Just depending, of course, on how extreme the values are in the data, your values of slope, correlation, all that would change by a lot. The other thing I also to make sure to mention is what happened with the correlation coefficient. The correlation went down to, or changed 57. It went up in this case, but in the previous line, it actually went down. So let me have all the lines, the new lines plotted, and the new correlation and slopes and everything calculated. So go ahead and pause the video if you need to copy and make sure your lines match up. But here's the new least squares regression line when you took the outlier out in the purple. You see how it's slightly going below on the left but above on the right, because again it's tilted like that. And the R value changed by 10% by 0.1 from the original to this one. So the relationship between the points, the correlation, the association became weaker. Now for the blue point, the blue outlier up here, the correlation actually increased. It actually went up by like 8%. The y-intercept changed a little bit, and the slope changed a little bit, like 1.5-ish. But what was it? The big thing? The big thing was like the correlation became stronger. Interesting enough. So when you're dealing with problems like these, there's not going to be a step-by-step method, and sometimes you're not really going to get the data in your calculator. I'll tell you that. You usually don't get the data in your calculator. You usually just get pictures of the scatter plot, and you're going to be told what multiple choice answer best represents what would happen to a point. So make sure you understand and think logically about this. But formally, when you get a problem like this on an AP exam, always like to write a complete, thorough answer. Because obviously I'm a teacher and I don't want to write just like a textbook would. So here's your long formal answer that I had here. So I advise you to write. It looks long, but it'll take you like maybe 6-7 minutes of writing. But here is the thorough explanation. And the first outlier that we took out, and it made the points, well, so that point, let me show you the picture so it can make more sense. Having this point here pulls the line closer, so then you're going to have a stronger correlation. So having that point there makes the correlation closer to 1, but that's why when we removed it, it became weaker, went down to 0.38. And also again made the line a little more flat, making the slope closer to 0, because it's like tilting it that way. Now for the other one, since it's high above the mean of x, the far, above the mean of y, is way up here, it changes the correlation. It makes the correlation weaker, but it doesn't really change, the slope by much, or it's not what we say influential, which is what we're going to look at next. So after we write that down, let's look at these next two definitions that this problem, basically gets at. So you notice I'm using this word influential. So when we're talking about scatter plots, we have outliers, but we have, outliers that could be influential, or we just say they're outliers. So outliers are influential or special outliers. So, typically an outlier, we say it's a point that lies outside the overall pattern. You could have points that are very far in the y direction, but not x, or very far in the x, but not y. If they're outliers in the y direction, but not x, again, like this one they have very large residuals, as you can see. But this one was an outlier in the x direction, but didn't really have any. It doesn't have a large residual, but still it's an outlier, which again is kind of counterintuitive because it's close to the line. So when you do have an outlier that will change the statistics, like what it could be the slope, the correlation coefficient, whatever, we say it's influential. Now, how we determine if it's a lot is going to be based on the problem. Like, how do we know? Like, is that going to be a lot? Is that a big deal? Depends on the problem. Depends on the context. So that'll be something you have to base on each problem uniquely. All right, now on the last, on this last page of notes, we just have little practice problems that give you an example. This, saying where we're talking about is correlation is not causation. You probably heard that in psychology, or you're going to hear it. But here we have, scatter plot that shows the number of firefighters at a fire versus the amount of damage, and you're like, oh, looks like the more firefighters there are, the more damage there is. So we would say like, oh, like there's going to be we could say that there's a medium positive linear association between the number of firefighters and the amount of fire damage. And then the mayor's like, well, then let's stop sending firefighters, because more firefighters mean there's more damage. The firefighters are causing damage. Now hopefully we don't have a mayor that thinks like that, because we all understand in real life it's not firefighters that are causing there to be more damage. It's just that there's more firefighters there because there's bigger fires. So you're gonna have bigger fires, causing more damage, and as a result, you're gonna need more firefighters there. So again, this is an example where it's not that X is causing Y. So again, use your common sense of the real world, because it's it's something a computer can't do. A computer program can only crunch numbers. They can't think about situations in real life context. Now, another thing that we want to be aware of is when we have scatter plots like this, no matter how smart or how wise or how good of eyesight you got, you're like not going to be able to predict correlation coefficients by just looking at scatter plots. You may get lucky on some here and there, but there's eventually going to be there's an infinite possible arrangements of points that can give you correlations. And there's no way you can actually figure out each one just by looking. That's why you need calculators and computers to do it. But let's say if I want you to think right now, guess what each of these would be. Like what would they be? Like, you think this is 0.7, think that's 0.5, think this is 0.01. Like, think for a second what you would guess. Now what they actually all are, and I say all are because they're all the same. They're all exactly 0.816. And you could do a computer program. If you don't believe me, try to crunch them out. But the bottom line is that correlation, remember, is just based on a math equation. It doesn't mean that these are strong linear relationships just because they have a high correlation value. You got to pay attention to the pattern, because remember, this is just based off of a calculation. So remember, keep that in mind. Use the combination of information you have to make sense of the data. So finalize our correlation regression wisdom, we say. Make sure you're the one that determines what the X or explanatory variable will be and what the response variable will be. Because again, the equations in your computers or calculators, don't know what to make X or don't know what to make Y. So it's up to you. It's up to you because the computer has no idea. And it does matter in real life, right? Because you're gonna have one thing lead to the other. And the second big thing, make sure you only use correlation and regression analysis for linear relationships. You can't use them for you can't. Well, that's a whole different course. But for now, when we're talking about a correlation coefficient, we have to make sure that we can say that there's a linear relationship between the data. If it's not a linear relationship, you can't. The correlation doesn't help you. Doesn't do nothing. It doesn't matter how strong it is. If we can't say it's a linear relationship, but between X and Y, correlation does nothing. And again, since it's just based on math, they're not resistant to outliers. So you have to make sure you look at the data, make sure that there's nothing that's causing the correlation to be very high or very low. Because sometimes it could just be one or two couple of values that could significantly change the value. And again, that saying that I mentioned like a minute ago, association does not imply causation. Even if you have a strong association between two variables, like maybe 0.9, you can't just be like, oh, well, since it's strong, that means X has the cause Y. That in itself doesn't mean that that's going to be true. It's not good evidence. You have to look at other stuff. Like there's a lot of correlations you'll find in real life data. Like there's popular correlations, that people who live longer have more cars. Oh, so it's like buying more cars causes you to live longer? Well, no, because people who live longer, first off, they're going to live longer, so they got to buy more cars because their cars will, not last as long. People who live longer tend to have more money, have better health, have more money to spend, that sort of thing. So there's all sorts of correlations that you could find just by Googling. Just the one I just showed you with the firefighters. But keep that in mind because it's a very common and popular saying you'll hear in psychology and other other areas of hopefully something you'll be studying down the road. All right, so there you go. Good luck.